learned about the definition of the tree, the graph, and connected branch or branch, linkage branch, or whatever you can use. And we have learned the inner relationship between the numbers of the branches and the nodes and the independent loops. And we also learned about the definition of a path, the loop, and the mesh. The mesh we have already learned it from the earlier lessons. And from there, we continue our journey from the perspective of topology of geometry. We try to talk about the inner constraints between the number of the independent equations that would solve the unknown variables in the circuit. And at the very end of the lecture this morning, we learned about the constraint of KCL using this kind of a topology. Then we know that the independent number of the KCL equations equals to n minus 1, right? So for a circuit with n nodes, it has n minus 1 KCL equations. And then we talk about the independent equations of a KVL, right? Similar to those constraints of KCL equations. We also know that if we list all the KVL equations for the meshes, for example, this morning we listed 4 mesh voltage equations based on KVL constraints. The first one, 134, this one. And the second one, 235, this one. And the third one, 456, this one. And we put this 3 together, we can 1, 2. We use equation 1 minus equation 2, then we could get U1, 2, 4, 5. U1, 2, 4, 5 is this one, right? So then we have this conclusion that we can achieve KVL equation in other loops through the addition or subtraction of more than 3 mesh equations. So which means the number of the independent KVL equations is also limited or constrained by the inner structure of this topology of this circuit. So let's have this conclusion. The independent numbers of the KVL equations equals to the number of the basic loops, and the number of the basic loops equals to b minus n minus 1. B is the total number of the branches. N is the number of the node in the circuit. So once we have a circuit, we can calculate, we can count how many nodes it has, and we can count how many branches it has, then we can reach this conclusion that the number of the independent KVL equations could be calculated by using this formula. So for a circuit who has n nodes and b branches, the independent KCL, KVL equations it has is limited with this number. So together, combine this, we know that the latter one is independent KVL equations, and the first thing is independent numbers of KCL, right? Wait a minute. This part is a independent number of KCL equations. This one is the independent number of KVL equations. Together, they made up of the total number of branches. So we know that for a circuit with B branches, each branch has its own current, and each branch has its own voltage. So at least we have to know if we want to solve the circuit with B branches, then we have to at least solve B voltages or B currents for each and every branch. So the total number is definitely is B, and it could be reached from least the n-1 KCL equations and list B minus n-1 KVL equations. So this is how we gonna achieve those B equations. So once we encounter a circuit and we would like to solve the branch voltage or currents in the circuit, we can list the KCL and KVL equations, and we can count the number of the KCL equation and the number of KVL equation. And if they don't match this conclusion, probably something wrong with the equation we list. Or if the number is less than this one, so that means there must be some constraint relationship we didn't notice. So we have to do it again to find the missing equation. Now we can talk about the branch current method. The branch current method, obviously, from this name we can see that it's based on the branch current. It's a current method, so we're using the current as the variable to calculate, and we also try to use this branch current to represent the branch voltage to fill in the KVL equations. So this is how we deal with it. We use the branch current as unknown variables to list the equations. So if we have a circuit of n nodes and B branches, And if we want to solve or get the branch current, so there must be B branch current. So there's the number of the unknown variables is B. So we have to list B independent circuit equation to solve this unknown variables of so first thing first, we have to write independent equations. First, we have to write the KCL equations. And we also know that the independent equation, KCL equation number is n minus 1. N is the number of the node. So we can randomly select n minus 1 nodes and list the KCL equations on them. This is how you do it. But in reality, if we look closer and look much carefully, we could see that some nodes are better than the other. And if it is connected to some kind of or is directly connected to a current source, something like that, then one branch current is already done. So in that case, we have to choose the n minus 1 nodes carefully to avoid unnecessary calculation. And the second step is to write the KVL equations. And we know that the independent KVL equation is B minus n minus 1. So we have to choose the basic loop column to write this equation. And to do that, we could list all the nodes and we make a tree. And we also know once you add the rest of any of the rest branches back to this tree, it will form a loop, and you add it back one by one, and then you can just list for that loop. But still, there are tricks in it. We know that if you select a different kind of a tree, you will encounter different kind of loops, and the KVL equations in different kind of loops are not as not the same level of hardness. So it is still a trick to choose the KVL basic loop to write the KVL functions equations. For example, see in this circuit we have a 1, 2, 3, 4 nodes, right? N equals to 4, right? So n minus 1 equals to 3. So in this case, we can write 3 KCL, right? Three KCL equations. And how many branches we have? 1, 2, 3, 4, 5, 6. 6 branches. So B equals to 6. And the KVL equation number is B minus n minus 1. N minus 1 is 3, B is 6, and this equation is 3. So together, they will form 6 equations to solve the branch currents. So we now know that we have 3 KVL equations to list and 3 KCL equations to list, right? So for node 1, we can have this calculation that I1 plus I2 minus I6 equals to 0. We know that I6 goes in and I2 and I1 goes out. So we give I6 a negative signal. And for node 2, you see I3, I2, and I4. I2 goes in, I4 and I3 goes out. So we give I2 a negative sign. And for node 3, we have I4 goes in, I5 goes in, I6 goes out. So we give I6 a positive sign. And that's enough. We now know that KCL number must equal to 3. So we have 3. So there's no need to list the node at the KCL equation at node 4. There's no need. And we can take the mesh as independent loop to write the rest of KVL equation. Now we know that the KVL independent KVL equations number is 3. So I have to find 3 loops. And this time we'll take the mesh as the independent loop and to write the KVL equation. So for the first loop, we have U2 and U3 minus U1. The U2, U3, U1. The voltage of resistor 2, voltage of resistor 3, and the voltage of resistor 1. And for the second loop, the voltage of resistor 4, resistor 5, and resistor 3. And for the rest loop, we have 1, 5, 6. Those 3 are consumers. And the consumer's voltage equals to the producer's voltage. So the producer's voltage is US. So now we have 3 KCL and 3 KVL, right? It's KVL equations. And this is the KCL equations, right? Now we want to know the current on each branch, right? So we have to replace those voltage expression by using the Ohm's law. So from the Ohm's law, we know that the voltage on the resistors equals to its current times its resistance. And we also know that if we take the reference direction, we know the what kind of a sign should put ahead of the those voltage it represents. So apply the Ohm's law. We can eliminate the branch voltage or replace it So we replace the branch voltage using the corresponding branch current. So you can see that R2I2 plus R3I3 minus R1 times I1. The first loop has been replaced. And the second one, the first one, and the third one. Now we have 6 equations about the branch current. Also, we can just directly omit this kind of loop, this step. We can just write the voltage on each branch directly, so we don't have to write this stuff. But if you don't, you're not very familiar with this, and you are not that skilled, we can just have this, left it here, and we do the replacement error. Those both all right. If you are very skilled in this kind of tricks, we can just directly omit it, the middle steps. So this is how we gonna solve it. We have 6 equations about 6 unknown variables. So that's enough to solve it. But that doesn't guarantee there's always a solution. Because if the number don't add up, which means this kind of a scenario will not happen in reality. So that could happen. So now we're only talking about the theoretical stuff, problems, scenarios. But in reality, if your assumption sometimes goes wrong, probably it will not reach a good solution. So let's summarize it. The general steps of the branch current method is, first thing first, we have to calibrate the reference direction of the current and its voltage of each branch. So before we do anything, we have to mark the reference direction on each branch. Once it's done, the negative sign or positive sign associated with the reference direction will follow all the steps all the way back to the solution. And then we select n-1 nodes and write the KCL equations. And then we select the b-n-1 independent loop to write the KVL equations. But if you select a loop, you better specify the loop path direction. And once you've done it, all the consequences, all the results are associated with this set. So we can use the KVL constraints to write it. So now we already know the number of independent KCL equations and the number of the KVL or independent KVL equations. So we can use this to calculate. By solving this set of equations together, they form a number of B equations of B branches. So solving these equations together, we will reach the final result. But in general, generally speaking, it's very laboring, of solving this kind of equations, set of equations manually, because the larger a set of your unknown variables are, the more difficult you're gonna encounter in the calculation. So it's not always that easy, but since we have computers, we can do something else to bypass it. And we can using mathematical tricks and other stuff to solve it. And we can use MATLAB to solve this kind of problem. So we have different kinds of solutions in the calculation. Once we reach the value of the current on each branch, we can calculate the voltages and other stuff, other unknown parameters in the circuit. So let's talk about the features of this branch current method. This branch current method is very useful. But its very foundation is still KCL and KVL equations. So if you don't remember this kind of a method, doesn't matter. You just directly write the KCL, KVL equations. As long as the number of the equations, the total number of the KCL and KVL equations adds up to the number of B, the number of the branches. Somehow you can reach the final solution. But if you are very familiar with it, sometimes we don't even think about the constraints, and we just directly write it, and it will do it. Let's see an example. Let's calculate the current of each branch and the power emitted by each voltage source. See, in this case, we have two voltage source, right? And we have 3 resistors. And since we have 2 nodes, right? In the number of the node equals to 2. So n minus 1 equals to 1. We only have to write one. We only have to write one KCL equation, right? KCL equation 1 about A. So we can have I1 plus I2 equals to I3, right? Because only I3 goes out and I1, I2 goes in, right? And we know that we have 3 branches. B equals to 3, right? And we know that B equals 3, B minus n minus 1. N minus 1 is 1. So B minus 1 is 2. So we have to write 2 KVL equations. And we can select a loop like this and this. And we also can select the overall loop. Anyway, you can choose it anyway you want it. So the first one, the KCL equation and KVL equation, loop 1, loop 2. We can write it directly, omit the the step of you represent the branch voltage with each branch. We don't have to do that. You know that for the first branch, we have this 70 voltage and 6 voltage 70 volts voltage source and this 6 volt voltage source. And we can write it like this, right? The voltage on the resistor 1 minus the voltage on resistor 2 equals to 70 minus 60. See, we have two voltage source, and their reference direction are not associated with each other. So if we take the 670 volt voltage source as positive, then the 6 volt voltage source must act as a negative source. And similarly, we can write the equations on loop 2, and we have also know that we also know that the voltage U equals to US. And we can do it like this by using the typical mathematical method to solve it. But this trick is not very pleasant. We know that you don't have to solve this kind of stuff because it's very liberating. So this is not a good trick we represent. We don't recommend this. So we can do it another way. Actually, for this example, actually we could do it whole new differently. You see that from the knowledge we have learned from last lecture, we can solve it by translate this into this one. The first loop 1 into a current source together with a resistance, and that is a 7 ohm resistance. And the second loop, we also could transform it like this. Transform it into a current source with a parallel resistor with 11 and you see that, right? And we also know that this part is I1 and this part is I3. So the current runs through the resistor, 11 ohm resistor, mass equals to, this is I1, this is I3, this is I1, I3, I2, right? So this one was going through a current that is I1 plus I3, I2 minus I3. Dot, right? Under this I1, we can directly solve it, right? This I1 dot is 70 over 70 is 10 ampere. And the other one is 6 over 11. And we know that these three resistors are in parallel connections. So we can put them together and calculate that. So this is another trick by using the trick we have learned from last lecture, and it's better than this kind of a calculation. So, but both kind of method are okay if you are familiar with one kind of method. You can solve it any way or not, one way or another. Let's take another example. This one asks us to write the branch current equation, and then this in this circuit we have this ideal current source with 6 ampere, and ideal voltage source with 70 volts, and let us write branch current equations. We know that have 2 nodes. N minus 1 equals to 1, and 3 branches. B equals to 3. B minus N minus 1 equals to 2. So we have 2 KVL equations and 1 KCL equations, right? So we can select point A, the node A, as a the node to write the KVCL equations. So we have I1, I2, I3. I1, I2 goes in, I3 goes out. So we have this stuff. And we already know that in this branch we have ideal current source. So I2 equals to equals to 6 ampere already, right? And since we don't know the voltage on the current source, we just assume it with a U, and we still can write the we can still write the as KVL equation from first loop, and from the second loop we have this. Now we have 3 equations about 4 unknown variables. We also know that this U is an unknown variable. So in order to solve this stuff, we have to add this information here. Right, so once we put this I2 equals to 6 in it, so then we have 3 equations about 3 unknown variables. I2 is known, and I1, I3 is unknown, and the voltage of the current source U is unknown, so we can solve it. But actually, that is not the most genius solution. We will have several other supplementary ways to do it. Actually, since we already know I2, so we don't have to write it like that, right? we can directly write the first the KCL equation on the node A. So we don't have to using the branch current retrieval to eliminate the I2. Then we only have to write one equations. In this loop, we don't have to think about the voltage of the current source. Right? So in this case, you see, if you're doing the KVL in this in this scenario, then we just avoid the calculating the voltage on the current source. Together, there are two unknown variables and two equations. In doing so, we avoid of calculating the voltage on the current source. So it is it definitely is a good way to write solve the problem. Right? Yin, are you following? I think this is not very difficult, right? Anyway, in this case, we all just using the very basic tricks we have learned, the KCL and KVL tricks. Its only difference is now we know exactly how many KCL equations and how many KVL equations we should list. All right. Let's see. Generally, let's see. So I think it's not very difficult to solve this. So then we can have another example, example 3. It asks us to column the branch current equations. So in this case, we have one controlled source here. This number is 5U. U is the voltage on the resistor 7, right? So still, we have two nodes, n equals 2, n minus 1 equals to 1. So 1 KCL. And obviously, we have 3 branches, B equals to 3, right? So we have to list 2 KVL equations, right? So together they will form 3 equations. And how could we deal with it? Deal with the control source? Although we don't know exactly the number of the control source, but once you have this U who controlled the signal U, you have this controlled voltage source voltage. So still we list the 2 loops KVL equations. For the node A, this point, all 3 stuff add up together to 0. So the KCL equation is done. And we can list KVL equations in loop 1 and loop 2. Those 2 are KVL equations. And then we have 4 unknown variables. 4 unknown variables and 4 unknown variable and 3 equations. So that's not enough to solve this problem. So we have to find an extra equation to solve the unknown variable 5u. We also know that u equals to the current I3 times the resistance of 7 ohm. So we now have four equations and four equations and for four unknown variables, right? So we can solve it. But actually, it's not that difficult, you see. In this scenario, we have a controlled source. But in this case, how to write the equations? There are two steps. First, we consider the controlled source as an independent source. And then we can just write the normal KCL and KVL equations. And then we write a supplementary equation to represent the constraints on the controlled source. So we can eliminate the unwanted middle variables, unknown variables like this u in this equation. So we replace it with the variables we are familiar with. So then this four equation set will degrade into three unknown variables free equation scenario. This is the typical step of doing it. So if you have a control source in your circuits, and in this case, we don't have to worry about that. We just list the KCL and KVL equations as normal, and we found a constraint equation that illustrates the relationship between the constraint controlled source and its controller variable. So then we can use the control variable to replace the controlled variable. And then we can reduce the number of the equation set, and everything go back to the just like the old time. This is how we deal with it. Of course, we have several other methods to do it, right? See, we can just transform this kind of stuff into, this is the first branch. This is a second branch. And this is a third branch. And we can calculate, we can transform this stuff into this. And we can calculate this, what current source has a current is 70/7. and this one is 7, and this one is 11, and this one is 7, and its current is 5U over 11. Right? And we also know 5U over 11, and we also know that we can replace this one with this one, and we can have another one to represent the total relationship between it is 3.5 ohm. And we can just calculate the total resistance of these two branches. So everything go back to its original form. So instead of listing the KCL and the KVL equations directly, we can just transform this kind of a problem into an odd form. Both are right. So if you have many tools, you can just choose what kind of steps you want. So let's take a 10 minutes break. Okay, let's go back to our lecture. So, you see that from the last lecture, we have introduced this tricks to transform this combination of series connected voltage source into parallel connection of a current source and a resistor. So we can also use this trick to simplify this kind of a circuit. So you see that this is a second loop, and this one is the first loop, right? We can transform it into this, and we can do the calculate. We can do the calculation anyway. So then we can go to the mesh current method. Mesh current method is very simple. We follow the mesh. This method, according this kind of a method is based on the assumed the mesh current to be the unknown variable to list the equations. But this kind of a method is only applicable for planar circuits, or it's only useful in two-dimensional circuits. So let's assume once we have a unified current, running smoothly in a mesh circuit. So we can calculate the voltage on each branch by using the combination of the current, the mesh current from the adjacent mesh. So now we try to explain it. The basic idea of this mesh current method is to reduce the unknown variables number. So let's assume that, imagine that in every loop there's a loop current, and all the branch current could be expressed or represented by the combination, a linear combination of the loop current. So instead of list the branch current directly, we use the mesh current, and using the combination of the mesh adjacent mesh current, we can also reach the branch current on each branch. So by using this kind of a method, we can still list the KCL and KVL equations. For example, in this, if we have this kind of a circuit, you see we have 2 nodes, 3 branches, and we assume that there's a current IL1, I loop 1, circulating the first mesh clockwise, and we have a I loop 2, IL2, circling the second mesh. And we can use this kind of a method to represent all the 3 branches current. Branch current I1 must equal to IL1, and the branch current I3 must equal to IL2, right? And the third one, I2. I2 could be considered as IL2 minus IL1 since the direction of IL2 is associated with I2 and IL1 is in the opposite direction to I2. So we give IL1 negative sign and IL2 positive sign. And so we can see all three branch current I1, I2, I3 could be represented by only two loop current, right? Instead of calculating three branch current, we're only calculating two loop current. So still we can list the KVL equation to solve the unknown loop current. And we also know that the number of the independent loops is 2. So we can select two independent circuits to express the constraints between the voltage and the currents in each loop. So since the mesh current is closed in the mesh and flows in and out once for each related node, and so the KCL is automatically satisfied. So we can just list the corresponding KVL and if we have a common branch, then we have to use a combination of the adjacent mesh current to represent that is the branch current in that boundary branch, and still apply the KVL equation. And we also know that the mesh current method is actually a special loop current method, and the number of the equations is the number of the mesh. Since we assume the unknown voltage, the unknown variable is the loop current. So if you have two loop, then you have two unknown loop current. So the number of the mesh is the number of the unknown mesh current. So how to list the equations? Still, for this example, we can do it for the first one. First one, we see I1, L1 its reference direction is associated with I1, so we can see that I1, IL1 is positive, and we see that for US1 is is in a unassociated reference direction, so we give it a negative sign, and for US2, the second voltage source, we see that the reference direction of the loop current is associated with this voltage, so we give it a positive sign. And for R2, we see that we know that this current running through it is because the second branch is a common branch, so its current is the combination of two adjacent loop current. So it's IL1 minus IL2 according to the circulation direction of the IL1. Since we are listing it in mesh 1. So its voltage is L1 minus L2 since those two are circulating in the opposite direction on branch 2. We can also list this kind of a KVL equation in the second loop, right? Second loop. Still we have ILR3, IL2 times R3, and this stuff. This time we see since we are circulating in the L2 direction, so L1 takes a negative sign. And we see that this time, since L1 goes in the negative polar, negative pole of the voltage source, so those two, the loop current and the US2 voltage are in unassociated direction. So their reference direction is unassociated, so we give it a negative sign. In this case, we have you see L1, L2 as unknown variables, and US1, US2 we already know, and all the resistance of all three resistors are known. So we can transform this kind of stuff into another form. Oh, see the first equation, we rearrange it, and we can see that before IL1, we have R1 plus R2. Oh, R1 plus R2. And minus R2, IL2. So in this case, IL2 is in the opposite direction, so we give it a negative sign. The second equation turns into this. IL1, since it's in the opposite direction of IL2, so for mesh 2, the IL1 part has a negative sign. And for IL2, they got a combination for R2 and R3 together. So you see that this is the voltage source in L2, and this is those two are the voltage source in the first mesh. So we can just directly write this kind of a equation instead of writing it like this. We don't have to write these two equations anymore. We can write this kind of equation directly instead of writing it from KVL equations directly. So although its fundamental, its foundation is KVL, but we don't have to do it all by the rule or by the book. We can jump it to the final conclusion like this directly, right? Using the second second set of equations to solve it. That's going to save us a lot of energy. And we can call the combination R1 plus R2 equals to R11. So is the R11 is the resistance in the first mesh. So the sum of all the resistance in mesh 1 is called the self-resistance of mesh 1. So R11 is the self-resistance of mesh 1. Similarly, we can call it R2 plus R3, self-resistance of mesh 2. Right? So R22 equals to R2 minus plus R3. So it's self-resistance in mesh 2. And together, they share a branch. So we call R2, a mutual resistance between mesh 1 and mesh 2. And since those two loop current circulating in opposite direction, so we know that their mutual resistance must be negative, so we give it a negative sign. And it forms the neutral resistance R12 and R21. So we can write it like this. And US1 is the net value of US1 and US2. So US loop 1, USL1 is the algebraic sum of voltage sources voltage in the first mesh. And since there's only one source in mesh 2, so US2 is the the voltage source in mesh 2. And do remember that self-resistance is always positive. So self-resistance, we see that the first one, R11 is R1 plus R2. And for mesh 2, its self-resistance is R2 time plus R3, and it's always positive. And the mutual resistance or the common resistance could be negative or could be positive. So if IL1 and IL2 they are going in the same direction, so in this scenario we give the mutual resistance a positive sign. Otherwise, if the R1 and R2 are going in opposite direction, we give the mutual resistance a negative sign. So that's how we define the self-resistance and the mutual resistance and the mesh voltage and the mesh voltage of the source. And also we know that if the voltage source voltage direction associated with the mesh current direction, we give it a negative sign. Otherwise, we give it a positive sign. So we see this one. We see this one. The IL1 is associated with the first one, first voltage source. So we give it this one negative sign to a positive sign because the current is associated with the second voltage source and in the opposite direction of the reference direction of the voltage source 1. So we can transform this kind of a method into a standard form. So we can list it like this: R11, R22 is the self-resistance is always positive, and R12 and R21 is the mutual resistance between two meshes. So they are identical. But if the circulation direction of the mesh current in those two adjacent branches meshes are identical, the mutual resistance have a positive figure. Otherwise, it will have a negative figure. And USL 1 and USL 2 is the voltage source, net voltage source value associated with the mesh current. So for a circuit which has L cells or L meshes, we can write this kind of set of equations like this: R11, R22, and finally, which is R1L. And we have R12, R21, and R1L, R1, like this. Not this. R11, R22, that's in the diagonal line, and those two identical. So this one and this one, this one and this one are identical. So it's a symmetric.
Hello. Vashi, we cannot see your screen. Okay, yeah, now.
So we see that the self-resistance are in the diagonal line. R11, R22, RLL, R1L, no, RL. This one is obviously is not not a correct number. You see that. Right. REL, R1L, R21, R22, R2L, right? And this one actually is so all the self-resistance are in a diagonal line. And we have R21, R12, they are the same stuff. And R1 and R1L is the same stuff. So we have a symmetrical matrix to represent the combination of the current in each mesh and its the self-resistance and the neutral resistance or the common resistance as you wish. So this is how we list this mesh current equations like this. So we don't have to think about this any longer. Once we have to, we have made up of, we have assumed the circling direction of the loop current. We can just write this kind of equations directly, and using this standard form. But do remember that the self-resistance is always positive. And the mutual resistance, it could be positive. That depends on the circulation direction. If the loop current, the loop currents on the common branch encounters and those two loop current flows in the same direction. The mutual resistance will give it a positive sign. But if the loop currents in adjacent meshes are running in the opposite direction, then we give the mutual resistance a negative sign. So one mesh could be adjacent to many meshes. So we could have many mutual resistance, but we only have one mesh resistance for each mesh. So to remember, when the current flowing through the two meshes with the mutual resistance has the same direction, we take positive sign for mutual resistance when two mesh currents flows in the same direction. Otherwise, we'll give it a negative sign. So it's very easy to remember. And also, we can see that the same stuff could be applied to the sources. But what if we have not a voltage source, but a current source in the loop? Then how could we calculate that? That is a good question. So let's take an example. See, we have a circuit with 4 nodes. And 6 branches. We would like to know the current I here by using the mesh current method. So we can select the mesh as an independent loop. So we can do this like this. And we assume for the first mesh, we have RS, R1. Okay, this one is got a little problem. For the first mesh, we have 3 resistance, and we just add them up together, which forms a self-resistance for mesh 1. And for the second loop, since L1 flows from this direction to this direction, and I2, the second loop current goes from this direction to this direction. So they are in opposite direction. So we give their common resistance R1 a negative sign. For the third loop, you see that also I3 going from this direction to this direction, and I1 going to this direction, from this direction to this. So I1 and I3, they are in opposite direction. So we give a negative sign before their common resistance R4. And we see that since the current runs out of the positive pole of the voltage source US, so we'll give it a positive sign. And for the second loop, we see that it has three resistors, R1, R2, and R5. So have it, and we just simply directly copy their mutual resistance here with the first mesh. And for the third mesh, their current resistance, current direction, we see that I2 goes from this direction to this direction, and I3 going from this direction to this direction. So they are going on the opposite direction. So we give it a negative sign before their common resistance. And since the second mesh have no sources, so we leave the right end of the equation to be 0. And we can calculate, we can list the equations in the third mesh. Still, we just directly copy this one here because their relationship is being done. And in the third loop, we have R5, R4, R3. Self-resistance always be positive. And we just copy this one here. So it's very easy to list the third equation because we know that the mutual resistance we already calculated in the listed in the first two equations. So the very last equation is very simple. You just copy those stuff, copy those mutual resistance, and you have only thing you have to worry about that is you have to list its own common resistance. This is how we list the mesh current in this example. And since we would like to know the current I here, and we know that it's combination of I2 minus I3. So since this direction, you see that this direction is associated with I2. So and in the opposite direction with I3. So we have I equals to I2 minus I3. So here we have four unknown variables, but we also have four equations. So this set of equations, four equations for four unknown variables, which we can simply easily to calculate. But this indicates one thing, that for linear networks without control source, the mutual resistance in this coefficient matrix is symmetrical. So we can see that we can call it a symmetric matrix. And if we assume all the mesh current to be all running in clockwise, or all be running in counterclockwise direction, their mutual resistance always be take negative sign. So for network, linear network like this, and which contains no control source, it's very easy to list this stuff. And if you follow this step by step, and we can calculate it directly. So let's summarize it. The is like this. First thing, we select the mesh to be the independent loop, and we assume a circling direction. Thus, we set the reference direction of the circling current that remains the same all through the very end of the calculation. The second step is taking the mesh current as unknown variables, and we write the KVL equations. And the third step is to solve those equations, and we can obtain the mesh currents. And all the other stuff, the branch current could be calculated by the combination of the mesh currents. And if we want to do other analysis, like the voltage on each branch, we can do, once we've solved the branch current, we can solve or calculate the voltage on each branch and all the voltage on specific components in specific branches. This kind of mesh current method is only applicable. It is only suitable for a planar circuit. So if I have a three-dimensional circuit, it will not be suitable to use this kind of a method. But the KVL and the KCL laws still stand, even for three-dimensional circuits. Because those kind of methods coming from the energy conservation and the conservation of the charge. So that is not constrained by what kind of space you're in, a planar space or a solid space or three-dimensional space. Then we can talk about the loop current method. The loop current method is very similar to the mesh current method, but only this time we don't select the mesh to be to list the independent equations. We can randomly, not randomly, but almost arbitrarily take the loop current equation, and how to select the loop is at your view. So let's talk about the loop current method. We assume there's a continuous current running through the loop in the basic loops, and we list the equations from KCL and KVL to illustrate the inner relationship between the branches, and similar to mesh current method, we can still using this method to directly list the unknown variables. So this is the basic idea of the loop current. So since this loop current is listing the KVL equations for the independent loops, this number is still controlled to be like the b minus 1, b minus n minus 1, right? So if you do not familiar with it, we have to go back to the lesson we gave you this morning. And this method has n minus 1 equations lies, then the branch currents method. So both methods are okay. But in this case, in this scenario, we don't have to calculate too much equations in our solving process. For example, we have this kind of a circuit, and we can solve the current I by using the loop current method. See, this time we didn't we don't select the mesh to list the equation. We here we list the loop current. So by doing so, we can just we can see that for the second loop, its loop current is actually the unknown variable I. Still, we can list the loop current. So by selecting the loop like this, we avoid loop the current I to be at the very boundary of two loops. So it's only at the boundary of one loop. So we can assume that loop has a current of I. Still, we can list it the mesh similar to the mesh current method. We can list the equations from the KVL equations. So for the first loop, you see the first loop, and it has a RS, R1, R4 as a self resistance, and it's circling in the same direction. In all those three loops are circling clockwise, so their mutual resistance must be negative. So those two mutual resistance must be negative. And the first loop has only one boundary resistance, R1, the common with the second loop, and two resistance, R4 and R1, to be boundary resistance to with the loop 3. So R1, R4, loop 3. And this is for loop 1. And for loop 2 is very simple. You see, we just copy this stuff here. And for the loop 2, we have a self-resistance of R1, R2, and R5, right here. And its direction is identical on the boundary resistance with the loop 3. We see that so R1, R2, those two are in the same direction with R loop 3. So their mutual resistance, we give it a positive sign. And the third one is very simple, right? You can see that we can write this part directly down here. And we can just write this part directly down here. And the third one is its own self-resistance, R1, R2, R3, R4 together. So we have three loop current and three equations. And by solving it, we can solve the I, right? I equals to I2. So by selecting this current cunningly, we see that there are wide of calculating I2 or I by using the combination of the two meshes. So this method is a more general form of mesh current method. So basically, mesh current method is just a specific application of loop current method. So they are not very different, but loop current method is much more general. So this is how we do it. So we can just write it in a standard equation like this. And for the circuits with L equals to B minus or N minus 1 loops, we can write this equation like this. And in the corner, in the diagonal line, you will see that this consists of all the still the same stuff. Same mistake again. Hmm? Oh, it's not one. It's the I know that. I didn't make that mistake. It's just but it just doesn't show it very clearly. See, this is the standard form of the loop current law. See like this. All the self-resistance are in the diagonal line, and let's see, this one and this one, they are identical. So this matrix, the coefficient matrix of this equations are symmetric for the linear system with no controlled sources. So still, the self-resistance is always positive. And the mutual resistance or the common resistance could be positive, could be negative. If the current flows through the two circuits of the mutual resistance are in the same direction, so that we would give it a positive sign. Otherwise, we'll give it a negative sign. So much for today. See you next week.
Okay, teacher. Teacher, please send us the PPT file.
Okay.
Okay, teacher. Thank you.
As well.
Oh, Allah. Oh. Faida. Hello. Faida.
কি অবস্থা?
कैसे বুঝিস নো আর তো মাথার মধ্যে গিয়ে বেগে
বুঝি নাই।
আর মাথার মধ্যে গিয়ে বেগে कैसे বুঝিস না?
না
ফায়দা মানে
সব
এটা
পড়তে গেছে।
হাগুমারা হাগুমারা হাগুমারা
আচ্ছা আমি পরে ফোন দেবো রাতে।
Mhm.